pleased to see that so many have been able to join us, whatever hour it is at your place. So the title of my talk, utilizing geophysical methods for mapping subsurface groundwater resources and assessing their vulnerability, is a very, very big subject, but I only have time to cover some of it, but I hope you'll find it informative during my talk. First, a little bit about myself. See if I can change the screen. I have about 30 years of experience working with geophysics, mapping all sorts of different targets during the years. Now I'm working with WSP, and I'm heading a small group of geophysicists here in Denmark. Primarily working with methods applied on land, and we have another group working with the offshore part. My agenda for today is that first I will talk about the groundwater cycle, and then move on to the geophysics as a mapping tool, talk a little bit about how we during the years have applied that in Denmark, and then moving over to show some examples of the methods and the results that we have gained. Finally, I will come up with some thoughts and takeaways based on this talk. So first, the groundwater, the mapping of the cycle of groundwater mapping, and I found this picture in the Danish Environmental Protection Agency's homepage. The link is in the bottom if you want to study it even more. But the overall sequence of knowledge gathering and refinement during the groundwater mapping circle is defined by the different steps. At first you start off with gathering all existing data and then move on and refining whatever you find during the cycle. And as stated, the geophysics methods is only one of a long range of disciplines and activities that's necessary to get this comprehensive understanding of the groundwater resources and vulnerability. One thing that I want to emphasize is that all these disciplines that is necessary to get this understanding, they are interlinked and mutually dependent. So please do not consider this cycle as a stepwise sequence. We have to share the information that we gather with each other, and the dissemination between the different steps is very important. It's characteristic that each steps are being primarily driven by subject matter experts that really are experts within their own fields of application, but seldom geophysicists are really knowledgeable when it comes to the rest of the steps. And it's very important for us as geophysicists to share the thoughts and choices that we make during the gathering of data, but also the processing and the results that we come forward with. So and I will come back to the points regarding to this. Then geophysics as a mapping tool used in Denmark. We really have a burning platform in that respect, that our drinking water is almost 100% supplied by groundwater, and very decentralized. We have more than 2,500 public water utilities spread around the country. On top of that, open land is really characterized by intensive farming, and the agricultural land cover more than cover about 59% of the total land. And that, of course, comes with a lot of intensive farming with chemicals used on the surface, and there is a risk of those chemical substances reaching the groundwater resource. And that we started seeing that in the beginning of the 1990s, and then general registration was put out, emphasizing that all the water utilities have to pay a fee per cubic meter of water that was extracted and then distributed to the consumers. And that fee was initially in 1999 set to 2 cents, but increased to 10 cents in 2013. And that might not sound like a lot, but this fee actually gave a revenue of a total 360 million euros in that period. And these figures, this amount was used exclusively for groundwater mapping. So this huge economic boost into this industry that, of course, generated not only very intensive groundwater mapping results, but also initiated a development of geophysical instruments, new software, new databases in order to share the software among different participants in the process. Also, standards and calibration procedures were put out. And the maps you see to the right is a comprehensive picture of the SkyTEM and ground-based TEM that was collected not only this period but until last year. So it's a pretty large part of the country actually being mapped by geophysical methods since the beginning of this century. What came out of this all these activities was that methods that measured the subsurface resistivity distribution, they really demonstrated to be suitable for the Danish geology, and thus also mapping the groundwater resources. And initially, the DC methods were very, very popular, but during the period, transient electromagnetics also became very, very popular and also employed on a lot of projects. In the beginning of the process, also universities started working on airborne methods, and the SkyTEM was initiated in the beginning of the period as well. Later, the TOW-TEM method was developed and used in subsurface groundwater mapping. To the right, you see the relationship between the electrical resistivity and the geological materials observed in the Danish context. And I will be using the colors, as you see here, in the later presentation of some results. So what you should pay attention to is that the blue colors representing the low resistivity values, representing the clay and maybe even saltwater, if that exists in the sediments as well. In the middle, you see those intermediate resistivities representing moraine clays or silts sediments. And to the right, you see the high resistivities in the red and purple colors representing sand, gravel sediments, and also chalk and limestone, which in the Danish context often represent the groundwater aquifers that we have. Just some of the methods used, not only during the primary groundwater mapping period from 1999 until 2015, but also after that. Initially, the TEM, the ground-based TEM methods, was introduced in the middle 90s by Aarhus University. Has a production of 12 to 16 soundings per day, and were applicated with 200-meter separation of each of the soundings. And a day you could cover something like 60 to 80 hectares in that period. Depth penetration, depending on geology and which layout that you use, but between 60 to 200 meters. From 2003, the SkyTEM methods, which is an airborne transient electric method, was developed and employed in the Danish context. The production is 300 to 400 line kilometers, and with a 100-meter line spacing, that equivalents 3,000 to 4,000 hectares. Again, depth penetration that will differ between which kind of system layout that you use, but something between 150 to 500 meters depth penetration. Again, depending on which geology is present in the site. Later in 2019, from that period, the TEM, the ground-based towed TEM method was introduced. With that, we can have a daily production about 40 to 60 line kilometers. And with a 25 to 35 meter line spacing, that equals 100 to 140 hectares. Depth of penetration vary, but between 80 to 120 meters. What was one of the results that came out of the intensive period of groundwater mapping was also the sharing of data. So the principle was that if the public pays for this data, the data should also be available to the public. And in that respect, a Danish database was developed that will hold all the geophysical data that is collected for groundwater mapping. And to give you an impression of this impact, I showed you to the right a map covers all the ground-based TEM as well as the airborne TEM that was collected until now. And to the left, I've taken out an area covering 20 by 30 kilometers and tried to put a little indication of which data was actually collected within this box. You can see that it varies very much in time, from early 20s to 2017, and also varies in which density. Of course, the SkyTEM data will have a larger density that ones that are the ground-based ones seen, for example, in this area. And there are 200 to 300 meters between each sounding. And that also gives you an impression of what is the possibility of which geological structures can be resolved with those data. To give you an impression of the results, I will take you through some depth slices. Here, one depth slice that is fairly close to the surface, showing the resistivity variation based of all these different geophysical surveys. You can see from this picture how the data coverage is. Again, the SkyTEM data comes up with a very dense coverage, whereas the ground-based one are with a larger separation in those areas. The Danish geology is so in principle in this area depicted by the sketch on the right hand side. From the bottom, we see the blue colors represent Paleocene clays, which have very, very low resistivity. But in these Paleocene clays, we experience that there are buried valleys that has cross-cut the Paleocene clays, and on top of this, we see glacial quaternary deposits representing different kinds of sediments, sand, gravel, but also moraine clays, gels, and meltwater clays. This picture represents something very, very close to the surface. You see there are some measurements up here which is not within this level, but has a lower terrain level as 40 to 50 meters. And then there is a large variety in resistivities. Moving further down, we see that the Paleocene clay is represented by these colors. They come into this level and is very, very distinct. But also some structures are beginning to be seen, like this one and also this one, which is these buried valleys that is filled up with sand and gravel sediments, which represent groundwater resources. Moving further down, you see that how these valleys, they're still very, very distinct, very visible in the data, but also as expected, they get narrower and narrower once we move further down in the geology. So the TEM and and there are also the SkyTEM method shows very efficient in mapping those buried valleys, and these are very important for the future groundwater, not only the present but also the future groundwater resources, as they as the topsoil represent a good filtering material for these resources, and as the upper parts of the groundwater aquifers get polluted by pesticides or other chemical substances, the very deep resources are very important to know. And you can imagine if these very in some examples, the very narrow valleys has to be mapped by drillings. This will be a really costly program, but with geophysics it's possible to pinpoint those valleys very accurately. So in general, the TEM and the SkyTEM showed very good results mapping those structures. But I also want to emphasize that there are other methods that are more focused on not so much the deep parts, but the most shallow sequence of the layering. And from within this area, I will show how the TTEM method was employed from the early 20s, and there are these surveys conducted within this box. And I was focused on the most southern one. In this area, the SkyTEM data was measured in 2003 with a line separation of between 100 to 200 meters, and the sounding distance that also vary from 20 to 40 meters. The TTEM data was measured in 2020 with a line separation between 20 and 30 meters, and the sounding distance was between 8 and 12 meters. And I'll give you some examples of how the data look like on two profiles. You can see the position on the map to the right. One should also be mentioned here is that all the black stuff, the black tracks, is actually what data was measured with the TTEM method, but during processing, noisy data and other data distorted by other sources than the subsurface were removed from the data set, and that's why the data set that's available for interpretation is the white dots that is indicated in this map. You see this linear structure passing through the area here is actually a power line, and that's why the data cannot be used here. So the data projected into the northern profile 1, you see on the top there is the SkyTEM data with the TEM soundings depicted. Remember that the colors here, the lower colors, the blue colors, they represent, in this case, Paleogene clays in the bottom of the profile, whereas what we're looking for, if we are thinking of water resources, we're looking at the red to purple colors. So in this sequence, the SkyTEM will pinpoint a rather thick aquifer in this part, and that should be tested if this was interesting for water extraction. And in this part, you wouldn't really be looking for water because the resistivity is so low. But with the TTEM, you get, and not surprisingly actually, but you get a very more detailed picture of how the subsurface looks like. So the layering that comes up with the TTEM is not really being resolved in the SkyTEM method, and especially when it comes to this end, where there may be even water resources in these small patches here, but the inclining layers in this end really not being resolved in the SkyTEM data. On the other profile, the groundwater resource is not really visible in the data, but there are some more layering that is visible in the SkyTEM data. in the TTM data, we see that there are actually high resistivities in this end, and there are probably two high resistivity areas here that is divided by a low resistivity layer in the middle, which for water purposes makes this structure down here interesting, if there actually is groundwater to be extracted down here because of the protective clay layer on top. To the right end, we see this very detailed and inclining structure that is visible in the TTM data, not really being resolved at all in the garden part. More detailed comparison can be seen from this plot where I put the SkyDAM soundings on top and the TTM in the back, where you can see directly. And as a general remark, the lower resistivity structures, you see the bottom of the quaternary sediments are pretty good results in both surveys, and there is a good agreement between the results that we see. But the upper part, the detail layering, that's only resolved in the TTM data. I will take you to another example of the application of geophysics. In this example, the objective is mapping of geology in order to evaluate risk for groundwater contamination at a well field. So in this particular site, there was an agricultural contractor that was using the site from 1951 until 2014, and in this situation, there is also a well field that is located 180 meters from the site. And what makes this combination interesting is that the soil samples around the site, they show that the heavy contamination with pesticides in the topsoil. So the local authority, the region, they were very interested in this, and they started a campaign with boreholes, 7 of them with depths more than 20 meters. And during this investigation, they discovered 2 washing sites that is polluted with pesticides, and also in the historical studies of the activities on the site, they showed that there have been some storage of barrels close to the building. The near surface water samples show the existence of up to 34 different pesticides and a concentration up to 65 microgram per liter, which is, well, that is posing a risk if you have groundwater extraction nearby. So from the overall picture, we have these 2 washing sites, and the question is, how can a pollution contamination of the groundwater, how can that spread and be a threat to the abstraction of the groundwater, which is at this site down here? So a geophysical survey was one way to resolve this this geology is to doing a geophysical survey, and the layout was initially quite larger than this, but due to sensitive crops and the landowners didn't really like us to drive on the fields. Only a smaller part of it was able to be surveyed. The TTM method was chosen, and we surveyed something like 50 hectares in one day for this survey. You can see on this map that this the blue dots actually represent that the data that was approved during the processing covers this area. We have a power line cross-cutting the area, so that nearly no data was available close to the site. And I want you to make some attention to this profile that is cross-cutting the area. On this profile, I have projected the TEM resistivity values. These are imported into a 3D grid, which enables that you can cross-cut settings crossing the actually measured line. and then you can get a good picture of the subsurface geology. Remember that the blue-green colors here, they represent clay layers, and the purple colors represent where aquifers can be found. But from the resistivity alone, it's not possible to see which kind of lithology they represent. The site is at this location, and the abstraction well further downhill, meaning from the site here, and then the abstraction well at this point. These geophysical results were geologically interpreted by the client, which is Central Denmark region, by geologist Flemming Jørgensen, well known to the Danish participants, I guess, in this talk. It's stated that the geological layers and on top, they represent quaternary glacial sediments, and the Paleocene clay comes out with these bluey colors. Also, this big structure to the left represent a buried glacial valley filled up with sand and gravel. You should note that this gray line crossing the profile actually represent the reliable depth of penetration of the data that's been measured. So the interpretation is quite solid on above this line, but should be taken with more care in the lowest part. Also, you should notice that the position of the polluted site compared to the geology. So the groundwater resources, they are in the limestone down here, and you see that the Paleocene clay that is between the actual polluted site and the limestone. So the abstraction well is pretty good screened according to the site. You can plot the data as a cross-cutting map instead. So the interval that is showed on this map is actually represented by this gray line on the profile down here. So to the left on the profile, that is the bottom of the map, and then moving from left to right is moving from south towards north on the map. So in this level, 30 meters above sea level, we have the Paleocene clays on this side, and then cross-cutting the buried valley, and then you see the Paleocene clay just underneath the polluted site. The position of the abstraction well is here, and then moving down to see some of the glacial deposits very close to the surface in the upper part. And this Paleocene clay is very, very clearly determined by the TTEM resistivity data. And that Paleocene clay will act as a barrier to separate the contamination close to the surface and the primary resource represented by the limestone in the bottom of the profile. And that means that any pollution that is on top of the ground will never reach, or never is a big word, but the risk of reaching the primary groundwater resource below the Paleocene clays, it's very, very low. Also, if there is a risk here, there is a risk that they can travel on top of the clays and maybe reach a small water stream that is on the northern part of this map. So from this study, it was possible to conclude that you shouldn't be worried about the contamination reaching the abstraction of groundwater, which is in the limestone, but maybe you should be concerned if the contamination will reach the stream up here and concentrate the further and future activities towards that risk instead of being worried about the abstraction well. Finally, some thoughts and takeaways from this talk. First of all, that the objective defines the method and the scope. It's very important that the geophysicists are taken into account when which method is to be chosen for the survey in order to extract these objectives that are actually being central for the survey. Large regional surveys, they return large regional structures, and in only a few cases they will also return some information of the detailed topsoil or very shallow structures. Be aware that what we have seen during this long period, and that we have been undertaking groundwater mapping, that instrument software and computational ability is constantly improving. That means that what may not have been possible 2 or 3 years ago may be possible today, or may be possible in the near future. Also pay attention that the devil is in the detail. The method and technique is to be chosen accordingly to the critical geological features. So if it's critical to know the general structure of the geology, then regional mapping is to be chosen. But if it's the detailed, very shallow structures that is important, then a more detailed and method has to be chosen, and also the line separation and the density of the data has to be very chosen accordingly. And then finally, the potential with geophysics, in my experience, is very huge. But the dissemination between different fields of techniques and also background is crucial. For most people not being a geophysicist, geophysics, that's a black box with an unfamiliar output. And it's very important for those who have the ability to understand the geophysics, that they will take the time to talk with non-geophysicists and explain what choices has to be made during the processing of geophysics, and also the ambiguity and equivalences that can be in the data, in order to get the full benefit of the surveys being employed. So that was what I've chosen to share with you today, and I'm open for questions. I can see there has been some already in the chat. I can pick some. One is being relative cost of various methods. Yes, not surprisingly, when you distinguish between method, it's depending on where and what you want to map. I can give you some general figures that from my experience you can take as a guideline, but of course you have to get a specific offer for merit. For SkyTem, I think some realistic figures, at least in Europe, that will be something like a 50 square kilometer will cost you about 140 to 150,000 euros. Comparely, if you want to map a site with GTEM, the smaller sites up to about 100 hectares, that will cost you about 10 to 15,000 euros, whereas the larger surveys, which with GTEM as such is about 1,000 hectares, will cost you about 50,000 or even 60,000 euros, depending on accessibility and the terrain conditions in general. I hope that answers your question. Accuracy of EM methods versus ERT. That's a large question, and that's really depending on site as well. Generally, EM methods are best in determining low resistivity structures, and most places the water aquifers is defined by low resistivity structures being on both sides of the aquifers. ERT methods are very good in distinguishing the whole range of resistivities, and but the main reason for employing EM method is that they are able to map in areas, so you can, if you have these line separation small enough, that you could get a 3D picture of your survey area for a significantly lower price that it will take to do the same with ERT. It says, what in your experience is the best way to prevent geophysics being seen as a black box? That is talking to people. I mean, explaining. Not. It's very important that you, when you do geophysics and when you deliver a report, there's not only just deliver the report, but that you take the time to describe the results for the receiver. Take them through what decisions you have been made during the processing and doing the inversion of the data. And also, if there are ambiguities in the data set, don't hesitate to share that with the receiver also. So being open, being curious of what these results are being used to, and talk to your client about how they see the world and how they see the results. That's very important. Yes, there's one more question. Oh, that's a very technical one. Something about how I weight my interpretations and how the interpretations are made. This from Setin Ikic. I will choose to answer that in the mail instead of taking this on the online. Then there's a question how geophysics can help for existing facilities. And with the existing facilities, I guess that it's meant that existing boreholes or existing water utilities. One of the main drawbacks of EM method is that it cannot be used in cultural developed areas. That means that it will couple to the to cables and power lines, whatever, metal fences and whatnot made of metal. So in open areas, open land they are really efficient and in mostly cases valuable to use. But in close to the facilities, that doesn't really give you anything. And in some cases, ERT can be used in those cases to give you some valuable results. I hope that answers the question. Otherwise, please come back. Yes, I think that was about that. Thank you very much for joining this session, and please don't hesitate to come back with questions if you still see one, and you can write me directly on the email that is on the screen. Thank you very much.
Thank you, Anders. Thank you, everyone. Have a great rest of the day.